Hi, kids. Happy Friday. I'm going to try to make a good recording of this video. So somebody's asking me about if they're going to miss a lot if they missed the last half. I'm going to try to make a good recording and put it up. I figured out how to edit the video on YouTube, so I'm just going to use that. So you can watch that then if you miss stuff. But yeah, you're gonna miss some stuff today. Hopefully the first half of class will cover most of the tough stuff, and then the second half will be you guys trying out the problems. So hopefully that'll work out well. We'll see how far I get. We shall see how it goes. All right, okay, who did I just let in? Dang it. Who was the last one to come in? Was that Sophia? Oh yeah, it was Sophia. So I'm missing Claire again. Nevada is sick today. Everybody else is here. And Sam, you made it, it looks like. Nice. Good job. All right. Let's see. All right. I'm going to say this. Anytime I tell a class that the stuff we're going to do that day is really hard, I kind of like want to warn kids ahead of time, like brace yourself. This is going to be really tough and really do a good job paying attention, et cetera, et cetera, et cetera. So I always tell kids like, oh my God, today, we're going to do Hardy Weinberg or we're going to do chi-square and it's going to be really hard. And then we get all done with it an hour later and the kids are like, oh, that wasn't bad. That was easy. And I'm like, oh. So I'm going to use that approach now. I'm going to tell you this is really hard. And then, okay, kids, today it's going to be really hard. You got to pay really close attention. So then at the end, you can tell me how easy it was. Okay, deal? Yay. All right, cool. Let's hope it actually works out that way. All right, we're not going to do the PowerPoint today because I'm just going to draw for you like I was at the whiteboard, just drawing with my marker. So I'll use MS Word for that. All right. Let's talk about diffusion first. So first thing we're going to do is, can we all have the cameras on in the beginning of class at least so I can see that people are there? Let's just make that a habit that every time in the beginning of class, we just all have the cameras on. That'd be lovely. Such lovely faces. So wonderful. Okay. Actually, something. Wow, how did I not see that? Okay, I actually have to do attendance real quick, so forgot to do that. Well, my computer's acting sluggish. You'll have to know if I'm breaking in or out, if you can even hear what I'm saying. I hope it's working. Oh, everybody's already, no? Hold on. Claire, all right. All right, let's talk about diffusion. So this will be a little bit of review from freshman year. So we'll start with easy stuff and then we'll get into the little bit more challenging stuff in a minute. So let's check it out. Yeah, let's do this. All right, I'm just gonna like freehand this and we'll freestyle. So let's see how it goes. You'll have to give me feedback if any of this stuff made sense. I'll try to do my best artwork for you. We'll see what happens here. Let's go with a pretty blue. All right, so we're just going to talk about regular old diffusion. So let's say I take some like, I don't know, Kool-Aid powder or something, or what's that little colored sugar cube or something like that. And I put it down here in the water, I drop it in. Let's say it's blue from artificial color. And it's, first of all, it has to be a fluid. We said that last time. Can everybody hear me okay? Yep, okay. Just shout or type or something, if it breaks up or whatever. Might have to switch computers, but hopefully I can stay here. I like this one a lot better. Okay, so this has to be in a fluid. So usually that fluid is water, but it could be another solvent like ethanol or something, or oil or whatever it might be. But here we got water. And diffusion can also happen in gases, so it could happen in air, but in, for our purposes, almost all the stuff we're ever going to talk about with diffusion has to do with liquids, and it has to do with water as the solvent. So we're going to assume it's just water, and let's assume this cube is sugar. Let's say it's sucrose, that disaccharide. When sucrose dissolves, by the way, it does not dissolve down into the single, like sucrose will stay a disaccharide, okay? So you got your glucose, you got your fructose, they stay together. So each particle of sucrose is this big giant disaccharide thing with two rings stuck together covalently. So that's the spiel there, but it does dissolve very, very well in water. It loves to dissolve in water. It's really hydrophilic because of all those OHs, all those hydroxyl groups make it polar in a lot of regions, and it dissolves very readily. Okay, so what'll happen is diffusion will happen from high concentration to low concentration. All right, so the concentration of the sucrose is really high around here where it dissolved, and it's very low here. So we got high down here, and we got low up here, which is kind of funny that high is on the bottom and low is on top, but I didn't really think about that ahead of time. And then it starts to diffuse from high to low concentrations, okay? And the reason why that is because there's a whole lot of sucrose molecules here, all floating around in there, and water is, because it's a fluid, as long as it's in liquid form, it's going to be in motion. The molecules are in motion, and they bump into the sucrose molecules, and they hit them and propel them in all different directions. Well, it can't go in this direction very far. It kind of gets stuck by the glass there. So the direction it's going to go is, is where I drew the arrows here. And, if you suspended this in the middle, it would go in all directions from high concentration to low concentration. I hope that makes sense. Give me a thumbs up feedback or thumbs down. All right, so far so good. We got that. Or, if I spill some perfume on the floor, pretty soon you start to smell it because there's diffusion from the high concentration of the puddle on the floor to the low concentration to where you're standing. It's going in that direction. If you wait long enough, eventually the sucrose or the perfume or whatever the thing might be, the solute, is going to be sort of evenly distributed in the container, and we call that equilibrium. Okay, and that can be sped up with stirring or mixing it all up, but if you just let it sit there, as long as there's a certain amount of heat present, in other words, the liquid is going to be a liquid, it's going to stay a fluid, there's going to be motion like that. All right, most diffusion though in biology that we discuss isn't just plain old diffusion through a liquid, without any barriers. Most of the time when we're talking about diffusion, we're going to be talking specifically about a certain kind of diffusion called osmosis, and that's diffusion across a membrane, or diffusion of water across a membrane specifically. So let's see how quickly I can get rid of this. I don't want to go too far because I want to get rid of my beakers, but here we go. All right, got rid of almost all of it. Yay, that didn't take too long. So we're going to be talking about cells and cell membranes, and we said that water can diffuse across a membrane, not super fast, but it can sneak across at a pretty significant amount, and it can go back and forth that way. And water does move across membranes all the time. It goes in both directions depending on the situation that the cell is in. So why don't we start by putting a cell now. We're going to draw the cell nice and big, like this. We're going to put it in really strong salt water, just as an example. Or we could do sugar. It doesn't really matter what the solute is. It has the same effect. So we got lots of particles of salt on the outside. We got a really high concentration of salt here. And I'm not going to draw this all over, but it's supposed to be really dense like this everywhere, okay? So we got NaCl, NaCl, high concentration of salt water. And in here, there's also a little bit of salt, but way less. Okay, so we say the inside of the cell is hypotonic, and we say the outside, the beaker water, is hypertonic. And tonicity, or the tonic part of it, refers to an ability of a solute to draw water, the ability of a solution to pull water, away from somewhere else, the movement of water. So, all right, so hyper means a lot. If somebody's hyperactive, they have a lot of activity, they're bouncing around all over the place. Hypo means very low, or a low amount or a little. Like if somebody is hypoglycemic, that means like a diabetic person. If they're hypoglycemic, they don't have enough blood sugar. Hypoglycemic means low sugar. Or if somebody's hypothermic, that means their body temperature is too low. Does that make sense? So in chemistry, you're going to run across this, you sophomores, and the seniors, you've already seen this in chem. When your teachers are talking about like what is it again? Oh, hypochlorite. Does that ring a bell? That ion? Hypochlorite means low amount of oxygen, and perchlorite, per is just short for hyper, means more oxygen. So anyway, in chem, you'll run across that same stuff. But hypo and hyper is good to know. All right, so what happens? Now, the way we explain the movement of water now is actually not super easy to understand. So I'd like you to pay real close attention. Because the first thing that we think about is that we think about, okay, molecules want to move from high concentration to low concentration. We have a high concentration here, it wants to go in. The salt wants to go in, but salt, unfortunately, well, actually good, it's a good thing, cannot go across the membrane. All right, so the salt it tries to enter, but it can't get in there because it's charged and the membrane won't let it in. So the salt will not go anywhere, but something's got to give. Something's going to be moving. So instead of looking at the salt concentration, let's look at the concentration of water, which is a really weird concept, because when we're talking about like salt in water, we're always talking about like the salt concentration in the water, because the water is the solvent. Or if we talk about like Kool-Aid or lemonade or something like that, we talk about how much sugar, the concentration of sugar in the water. Well, now we're talking about the concentration of water, which is odd. So let's take a look here. The concentration of water can be determined by how many water molecules do we have in a certain volume. Okay, so if we look at like this volume right here, let's say 1 milliliter, we have a whole lot of water molecules and we only have 3 salt molecules. So I'm just going to make up numbers. These are not like accurate numbers. I'm just to show you. If we have 3 salt molecules, we'd have 97 out of 100 water molecules. This is just made up, okay? Just random numbers. But I want to make it out of 100 because it's easier to understand it then. Okay, so here inside of the cell, we have 97 water and we have 3 salt. And yeah, I know it's sodium and chloride and there's no such thing as a salt molecule or whatever. I understand that, but I'm just going to say it that way because it makes it easier to understand later. Out here, if we take 1 milliliter right here, I take the same volume, I count the salt particles. 1, 2, 3, 4, 5, 6, 7, 8. Here we have 8 salt, which means we'd only have 92 water. Okay, so we have 92 water and 8 salt on the outside. So the concentration of water inside is 97 and the concentration of water is 90 on the outside is 92. 97 is greater than 92. So the question then is, which way is the water going to move? It's going to go from high concentration to low concentration. So you guys shout it into the mic like you mean it. I want to hear everybody at once like a choir of angels. In or out?
Out.
Oh, I got to turn my volume up. Sorry. I had the sound all the way turned down. You got to do it again. Sorry, I didn't hear it. In or out?
Out.
Out. That was a beautiful choir of angels. That was amazing. Because water's going to move out, and so basically another way to look at that is to think that the water is following the salt. That's another way to think about it. The water goes to the salt. I noticed that sometimes that water does that. When I have a bucket of salt sitting in the garage for like putting on the driveway when there's ice, there's always, well, we're not on plasmolysis yet. We're going to get to that. So slow down there, Cadenze. Anyway, when I have a bucket of salt sitting in the garage, it always like starts to accumulate water. Like eventually there's like water on the bottom because the salt literally draws the water in, even out of the air. It's weird. It's not exactly the same thing as this here, but it kind of reminds me of that. All right. Okay, so water's going to pull out, water's going to get drawn out, and then eventually Katie, you can tell us what happens, please. You know this.
Wait, like out loud? Wait, who are you talking to?
Don't you go by Katie? I'm trying to be like cool.
Yeah, but you never call me that, so I was caught
Cadenze.
Plasmolysis or plasmolysis.
Thank you for saying it that way. Okay, so what happened to the cell, everybody? It shriveled up. Okay, so we say that's plasmolysis, plasmolysis. It's destruction of the cytoplasm. Lysis, you know, sometimes means splitting, destruction, killing, whatever. It's destruction of the cytoplasm because all the cytoplasm is gone now, it all diffused out, and it caused the cell to shrink. This is for an animal cell we're talking about right now, by the way. This is animal cells, okay? Not plant cells. We'll get to plant cells in just a second. All right, so that's exactly what happens. Now at the end, what you're gonna do is take a look at the concentration of salt on the inside. There was a certain amount of salt on the inside here to start with. That salt is all still here. But now look, the salt that was in there is all squished together in this tiny space now. So now when we take a look at this and we count, we see that, now there's 8 salts and 92 waters, which means now it's the same as out here. Okay, so it shrinks all the way to the point where the inside is equal to the outside. We say these two are isotonic. Isotonic means they're both the same concentration now. We don't have a higher concentration on the outside anymore, because if we did, the water would keep diffusing. So if we're really at the end of it, if we waited until there was no more net movement of water, then the inside would be the same as the outside. Everybody with me? So what happens to you when you drink salt water and you're stranded on a desert island, you're drinking salt water? Is that a good idea? Like you're super thirsty, you've been like, you know, you're all feeling dried up and I gotta drink something, so I'm gonna drink the salt water. What does that actually do to you? It
dehydrates you.
Dehydrates you, it draws the water. Does this help when I do this? This is helpful, right? This teaches you everything. It draws the water out of your cells. It actually dehydrates you. So that would kill you. Drinking salt water is a real fast way to die. That's not a good idea. Bad idea. Okay, so plasmolysis. Any questions on that? Good to go? I'm sorry that I don't have subtitles on this because it's Word and it works a lot better for me to draw than PowerPoint. Amra, are you able to follow along?
I'm good.
You okay?
Yeah.
All right. I can switch to PowerPoint if you would like, but for now, I'd like it better this way, but I will do that for you if you tell me.
Yeah.
So if you change your mind, just shout it into the mic and let me know, okay?
It's less torturous for you to not use PowerPoint, so it's fine.
I did not hear what you said.
It's less torturous for you, so I'm fine with this.
Oh, so you're being nice to me. Thank you. That's the first time ever you've been nice to me. Oh my God, this is a new beginning here for us. It's incredible. Okay, now let's do animal cell again, but this time let's put it in pure water. So animal cell again, la 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 la. And actually, I'm going to change the color. I don't want blue. I want let's do a realistic animal cell color. Here we go. All right, so animal cell again. This time, DH2O. What does that mean? DH2O. If you see that abbreviation in chem, what does that mean?
Isn't that like pure or something?
Pure, but that would be a P, and this is a D. So what does the D stand for? Really? No one?
Distilled?
There you go. Distilled water. Very good. You guys are so advanced. I'm so impressed. In other words, pure water. Pure water in there. All right, so just water, no solutes at all. In other words, if I'm counting my water molecules in my, volume here, I've got 100 water and nothing else. It's just water. Okay, in the cell, we said we had some solutes. We had some, sugar, salt, whatever we're talking about, doesn't really matter. So the cell now might have, what did we say before? It was like 3. Let's be consistent. Yeah, so we had 3 salts in the cell and 97 water. Once again, the salt cannot get across the membrane. It tries to diffuse out. It wants to diffuse out, but it can't get across the membrane. So I'm going to get rid of that. And the only thing that can move is water. So now where's the concentration of water greater? Is it greater on the outside or greater on the inside? Concentration of water, not of salt. What's greater, 100 or 97?
100.
100. So it's going to go from high concentration to low concentration. So it goes from the outside in. So the movement of water now is in. By the way, the cell now is hypertonic. And you're like, oh, wait a minute. You just told us the cell is hypotonic. You're lying. It's always compared to another solution. Now, if we're comparing it to a different solution, this is now hypotonic. The outside is hypotonic, low solute. The inside is hypertonic compared to the outside, higher solute. All right? Coolness? If this is an animal cell which has a flimsy cell membrane, which is kind of weak, it's not like, reinforced really strong, especially if it's like a red blood cell, it doesn't even have an ECM. ECM, anyone? I'll be impressed if you tell me. You should know this from chapter 6. What's ECM?
Extracellular membrane or something like that.
Extracellular
Matrix.
Matrix.
My bad.
Well, you were close, so you're almost there. All right, so now we wait a few minutes. We wait a little while for something to happen. Because that membrane is weak, the cell is now going to swell. It's going to get much bigger. It's going to sort of expand, and a lot of cells can't actually do that. Like a red blood cell can't expand like that. So instead of expanding real far and getting bigger, it'll literally
Explode.
explode. It'll burst. I'm going to burst. We call that process, I'll write it, you shout it as soon as you know it. No one?
Cytolysis.
Thank you. Also, you could say cytolysis. That's not how it's pronounced, but it should be pronounced like that because cyto means cell. Lysis means destruction or bursting or splitting. That's exactly what happens. The cell bursts open from this tremendous pressure on the inside. Okay, if I was going to then measure the concentration of solute in here and the concentration of solute in here, what would I realize at the end when this is all burst open? And I waited long enough. And then I went in here and measured this. How much salt would there be left in here?
Shouldn't it be equal?
Yeah, it should. So in other words, very
Little.
very small amount or not none, maybe, You might say, well, there was some salt, it should be all distributed, true, but the cell is so small compared to the beaker. If you look at the beaker, the actual cell would be like that big or smaller. So the amount of salt it's dumping into the beaker is nothing. This is like you going to Lake Michigan and peeing in the lake and then saying, aha, Lake Michigan is now salty because I peed in the lake. So now therefore, no, you made no difference. By the way, don't actually do this. Like, you're going to get arrested. Don't do this. Sam, stop it. I know you're going to go do this now. Don't. All right. Anyway, what am I missing here? Cytolysis, pure water. Okay, this actually happens in red blood cells. You can put them in pure water. Other cells in the body don't necessarily burst because they do have an extracellular matrix, so they're a little bit more, strongly reinforced. They have other cells around them, but they would then expand. They would swell a little bit. Kind of like cells on your skin. Like, how you get raisin fingers in the pool or whatever, or if you're in the bathtub too long. It's kind of like, they're absorbing water and they're swelling up a little bit. Okay, anyway. Hypertonic, hypotonic, okay, good. Cytolysis, cool. Now I gotta undo all this because I gotta, oh no, Okay, let me do something. Hold on. I'll just open it clean. Oh, that's the wrong one. Empty beakers. Where's my empty beakers? There we go. All right, cool. Let's do plant cell now. By the way, you guys with me so far? Is everything good here? Easy or hard so far? Oh yeah? Sideways thumbs? Ouch. Oh, okay. Noah Washburn, what say you? Is he frozen? Noah Washburn, you frozen?
Yeah, you like cut out for me. What?
Oh, you cut out for me. I was about to start singing the song from Frozen. Let it go. But actually, no, it goes. I should let it go. All right. Plant cell. Plant cells aren't actually green like this. Okay, so that's actually not like realistic or anything. Plant cells, the cell wall is not green, so I shouldn't really be drawing it green. It's the chloroplasts that are green, but you know, let's make it green because of plant cells, whatever, cool. All right, plant cells, we now have a strong cell wall on the outside. They have that square shape, much stronger, much better reinforcement than animal cells. Let's do the same thing. Let's put it in salt water. So in other words, hypertonic. High concentration of salt, lots of salt on the outside. What's going to happen is water is going to diffuse out again towards the salt, just like before, except now the cell wall is so strong, it's just going to keep its shape. It's going to stay a rectangle like that. And what's going to happen is, so water is going to diffuse out. What's going to happen is here, you're going to see the cell wall remains just like that. And then the cell membrane on the inside starts to pull away. So there is a cell membrane here. By the way, that's something about plant cells you need to realize. There's a cell membrane on the inside pressed up against the cell wall. Like you can't distinguish it even under a microscope. It looks like it's just all one thing here, but people think that, oh, plant cells have a cell wall instead of a cell membrane. No, 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 no. They have a cell wall on the outside of the cell membrane. They have both. So what happens is the cell itself is the cell membrane. That cell wall is like extra on the outside, reinforcement, you know? So when the water leaves and the cell shrinks, the cell membrane starts to pull away from the cell wall and starts to shrivel up in the middle like this. So we call that plasmolysis also. And all the chloroplasts and all that stuff are going to be stuck in here now. So let's go green again. We'll make those green. You know, all your chloroplasts and things are in here, whatever. But that's the difference between animal cells and plant cells. Basically, exactly the same thing happens. It's just that this shell of a rectangle stays behind, this cell wall stays behind, and it looks like this big different thing is happening, but it's not. It's the same thing. The actual cell itself is right here now. It's all shriveled up, just like the animal cell would have. The reason why this happens is because the cell wall is porous and it allows fluids and water and salt and everything to go through in both directions. It's not a problem, which means right here, we now have concentrated salt water. Right outside of the cell, we have concentrated salt water. Okay. And obviously here, it's going to shrink to the point where the concentration of salt inside is the same as outside. It's going to be isotonic at the end. So if you have road salt on the side of the road, gets into the grass, or if you dump salt on the lawn on accident, or too much fertilizer, which is a kind of salt, like, you know, potassium nitrate is a type of salt. You dump too much fertilizer on your grass, what happens?
It's dead.
Well, it's pretty obvious when I say too much. It's too much of a good thing is going to be bad for the plant. It's going to kill the plant. So you get brown spots in the grass where it all dies. If other plants are, you know, exposed to salt, they're going to die because they dehydrate just like you would if you drank salt water. They'll dehydrate. Okay. Any questions on that. By the way, the inside was hypotonic in the beginning. And then at the end, we are in an isotonic situation. I don't know why I wrote it like that. What the heck happened there? Where they're both the same. All right, one more. Plant cell again, la la la, da da da. I'm not going to draw as much this time. Pure water, okay, so distilled water. So hypotonic. And the inside is now hypertonic. Okay, which way is the water going to go? Is it going to go in or out? Shout it out together. 1, 2, 3, shout.
In.
Go in. Water's used. Who said that? Max Egan. Is that Max? Don't admit it because you'll get in trouble.
Yes.
It was him. Don't admit it. All right. Anyway, water's going to diffuse in. That's going to cause this whole thing to swell. Now, oh, it's going to burst. It's going to do cytolysis. No, the cell wall protects it. Cell wall is so strong that it can stretch a little bit and it just holds it in like almost like a, you know, like a canvas kind of a deal. So we got a lot of pressure in here now from all that water diffusing in, and we call that pressure Turgor pressure. So this is actually normal for plant cells in the normal healthy state to have a little bit of pressure on the inside, which is called Turgor pressure, and it keeps the cells rigid and strong. It keeps them inflated and nice and tight. It makes the plant stand upright, nice and strong. If you have flowers in the garden or whatever, nice, you know, not let's say a wooden tree or something like that, but like soft plants, herbaceous plants, if they dry out, they start wilting and they start sort of collapsing because the Turgor pressure is gone and it doesn't hold them upright anymore. Okay, so a little bit of Turgor pressure is normal. Now, obviously, if we put the plant cell in distilled water, that pressure would go up even higher than before. Anyway, so far so good. All right, cool. You might remember the potato lab that we did freshman year. I think all the other classes did that too, even if you didn't have me. You probably did one with potato sticks. We soaked them in salt water or fresh water. I know regular bio did that also. Whoever your teacher might have been, but the potato sticks you put in distilled water, they actually gained mass. They increased in mass because the water diffused in. And the ones we put in salt water, they shriveled up a little bit and they got floppy and they lost mass. So it's because of that. Alrighty. So this needs to be crystal clear in your brain, all of this, for us to to go on to this next part now. And this is the hard part. Up to now was like freshman bio. So let's give it a try. You guys ready? All right, cool. Let's do this. So there's another angle that we can take, another approach to explain everything we just did. The way we explained it the first time just now was by talking about the concentration of water. We talked about the concentration of water, which is kind of an awkward way to phrase it, but it's accurate. It's okay to, it's appropriate to say it like that. Because we're talking about the amount of water molecules in a certain volume. That's what concentration is. Now we're going to approach it from a different angle. We're going to talk about it in terms of water potential. So water potential is the ability of water to, like the force on the water, I should say, that moves it across a membrane, that moves it from one place to another place across a cell membrane. And there are two different components to water potential that influence this, which we're going to take a look at now. So water potential is abbreviated by the Greek letter psi, which is like a pitchfork like that, which kind of makes this whole thing scary because it looks like a scary symbol. And then people are like, oh, automatically this is going to be hard because it has a weird symbol I've never seen before. Well, maybe you do know your Greek letters, but that's just all it is, like a U with a line through it. Okay. So that's the symbol for water potential. Total water potential. the formula we're going to use is that water potential is the sum of the solute potential, psi sub s, plus the pressure potential. Now, this equation looks scary because it has that funny Greek letter, but in real life, it's not that scary because this is kind of like saying A equals B plus C. And that's like stuff you learn in middle school. Like that's not hard algebra. I just turned the chat off and now there's chat.
Wait, what does the P stand for?
Pressure, sorry, pressure. Wave functions, okay. Don't trouble me with the lesser sciences, please, okay? Here we talk about the epitome of all the sciences, biology, so don't bother me with physics and chemistry. You know why physics and chemistry exist, right? You know why they exist. They exist to serve biology. That's why they're there. Ryzen, what are you on about? Good morning, everyone. What? You just woke up? GM? What are you on about? Anyway, okay, I'm turning the chat off. This is annoying. So A equals B plus C, super easy. Stop it with the chat now. Enough. You guys, I can't help but look at it. I keep getting drawn to it. So every time you type, I keep looking over there. So stop it. I can't help myself. Okay, I'm going to undo this and we're going to talk about, oh, it won't let me undo it. Undo. Ah, no. What? What the kringle? Oh, I can't like erase just a little. Yes, I can. Yes, I can. If you only try hard enough, you can do anything. That's what my mom told me. All right, so this is solute potential. And solute is the stuff that's dissolved, like the salt or the sugar, okay? And pressure potential. And this is water potential, total water potential. So let me tell you some stuff about solute potential and pressure potential that I hope is going to make things a lot easier for you, because when I first learned this stuff, I was confused, but I didn't have anybody to teach this to me. So I'm going to try to like have you guys avoid the struggles I went through by just telling you some tricks right away. Solute potential, first of all, is the greatest it could ever be is 0. In other words, it's negative. It's always going to be negative or 0. It cannot ever be positive. And what that means is that solute can only draw the water to it. It can pull. So I'm going to say it pulls the water. All right, like salt will pull water towards it, sugar will pull water towards it. It can't ever push. Pressure potential, it can either be 0 or it can be positive only. Because water pressure pushes the water away. Like if you squeeze a water balloon really hard, it's going to push the water, like it might explode and push it in one direction, or it might bulge in a certain direction. It can only push it away. By squeezing, you're going to make the water go a different direction. It's not going to pull it towards you. It's kind of like when you push somebody, they're going to go flying away from you instead of coming towards you to give you a hug. So it pushes, like it pushes away. Everybody still with me? Okay. Now, sophomores, you haven't learned this yet in chem. Seniors, you have, and this is okay. I'm going to teach you, I'm going to just tell you some real basics about pressure. That's really all you need to know. You just need to know that pressure is like a pushing, right? Okay, like if there's air pressure on you, like if you're flying in an airplane and you're landing, or you're driving your car down a mountain, your ears start to hurt. You can feel the pressure in your ears. That's air pressure pushing in on your eardrum. Okay, that's really all it is. But pressure is one of those weird things that's measured in a lot of different units. Like every part of science, whether it's physics or chem or bio or engineering, they all have their different units. Like on your tire, on your bicycle or on your car, it's PSI, pounds per square inch, but that's English. That's not like metric system. So we don't use PSI, but that's one way to do it. Another one is atmospheres. That's just like at sea level on Earth, the pressure of the air above us, the atmospheric pressure is 1 atmosphere. So that's just like a standard that people use. And there's lots of other units that in chem the kids learn about, like torr and millimeters of mercury and stuff like that. We're not going to worry about those. We're going to use the unit of bar. Okay, so 1 bar is almost 1 atmosphere, 1 ATM. Okay, so it's almost like the amount of pressure that the air above us puts on us if we're standing at sea level. Okay, so the unit we're going to use is bar, but I'm not actually worried about the unit that much. Like, I don't really care that much if you know what a bar is or whatever. I just need you to know it's a unit of pressure. It's how much it's pushing, okay? How much pressure there is. As a matter of fact, when we do our calculations, I'm not going to put the unit in half the time. I'm just going to put the numbers in, because when we make drawings, it's easier just to put the numbers in without writing bar every time, but that's the unit we're going to use. We could be doing these calculations in ATM or in millimeters of mercury or pascals or PSI, but the standard in biology is bar, and that's what most textbooks use and scientists use, so we're going to do the same. Like on the AP test, that's what they would give you. They would give you bar. So that's what we're going to do. All right, cool. So let's check out a situation here. I got this other spiel here. Yeah, let's do this. Yeah, let's do, why am I doing plant cells first? Should we do animal cells first? Yeah, let's do animal cells first. Why not? Okay, so we're going to do the animal cell that's in salt water here. You can tell it's the one that's in salt water because it's shriveled. So we kind of have the punchline ahead of time already. You know, plasmolysis is going to happen, all that stuff, yada, yada, yada. Okay, cool. New color. So it's really concentrated salt water. So our solute potential has to be positive or negative. So psi sub S, solute potential, what do you guys think? Positive or negative if we have a lot of salt present, based on what I just told you?
Negative.
Listening. Negative, very good. Well, how much number do we make up? Like if I'm asking you to make up a number, you don't really know what, like, do you go to negative 10 million? Do you go to negative 0.5? I'll tell you a reasonable number for a salt solution, like a fairly concentrated, you know, salty solution like ocean water or whatever might be something like, I don't actually know what ocean water is, but it's in this ballpark. So we're going to say that the salt water here is like negative 12 bar. That's all I'm going to write is negative 12, but I'm talking about bar or bars, plural, okay? So that's our solute. Our pressure is just atmospheric pressure. It's whatever the, you know, atmosphere above us pushes down on us. I'm just going to say that's 1 bar. It's 1. Now, it's not going to be exactly 1. It's going to be like 0.95 or something like that, because we're not at sea level. We're here in Greenfield at like 800 feet above sea level. So our pressure would be a tiny bit lower than at sea level, but I don't care. It's close enough. I'm going to say it's 1 bar. All right, that makes it easier. All right, so then our total outside water potential is going to be solute potential plus pressure potential. So can you do the calculation for me? Negative 12 plus 1.
Negative 11.
Negative 11 is correct. So now we got negative 11 bars on the outside. Still with me? That's our water potential on the outside in salt water, negative 11. Okay, inside of the cell, I'm just gonna like cheat and tell you what it will be, because you have no way of knowing this, not having to. Okay. All right, thanks, Vance. I'll try to do a good job posting this. I might have to do it on YouTube. I'm supposed to use EduVision, but it won't let me edit. So I'll do my best to post this video, okay? All right. So the cellular fluid, the cytoplasm, is not at 0. It's not at 0 solute. It has sugar, it has salt, it has a bunch of stuff in it. I'm going to just make up a number. It's going to be, you know, quite a bit less concentrated than this horrible salt water. So we're going to say it's negative 3. Negative 3 bars. That's actually about what a plant cell is. Like a lot of plant cells are like somewhere between negative 2 and negative 3. That's actually where they are. But I only know that because I've studied this stuff or whatever. So you're not supposed to know that. Just have to trust me on it, okay? The pressure on the inside, oh wait, this is not a plant cell. This is an animal cell, but let's go with animal cell. The pressure on the inside is also going to be 1. So here's the part you might be like, oh, how do you know it's 1 on the inside? Anybody want to take a stab at it? Keep in mind, there's an animal cell. How do we know the pressure inside of the animal cell is 1 without having to shove a pressure probe in there and measure it?
Because it's at the same atmosphere as the beaker.
Yeah, it's going to be the same as the rest of the water in the beaker, because if it wasn't, like let's say it was less, what would happen to the cell? If the pressure inside the cell was less than on the outside would be, It would be,
Triple?
yeah, it would push on it. It would compress it. You know what I mean? And if the pressure in the cell was higher than the outside, it would,
Expand.
right. And it's not doing any of that. It's just sitting there. You know, well, it's not, it's going to do something. But when, I'm saying when we first drop it in, the pressure is 1 because it's just going to be whatever air pressure is, because the cell membrane will just conform to whatever the air pressure tells it to conform to. It'll expand or shrink to whatever it is going to be, and it's going to be the same. Okay, so in the beginning, this is going to be 1, and this is 1. Okay, that's kind of boring. Well, let's look at the total inside water potential. -3 plus 1.
-2.
-2. So now we can say that water potential in is -2. Water potential out is -11. So here's where it gets a little bit tricky. You got to have your math hats on now. Math hats? Is that even a, I don't know why I said that. Okay. Which number is greater? And everybody's like, oh, 11. 11 is greater. Which number is greater? Let's try that again.
-2.
-2 is greater. Like if I owe the bank $2, I am richer than my brother who owes the bank $11. Does that make sense? If I'm $2 in debt, I'm actually richer than the guy who's $11 in debt. So then I have more, well, neither one of us has any money, but I'm still richer because I owe less. And that's basically what this is. -2 is greater than -11. Water will flow from high water potential to low water potential. I want to write that down, from high water potential to low water potential. Because water potential is basically a push on the water. Okay, so if water flows from high to low water potential, it's going to go from high, which is -2, to low, which is -11, meaning the water will flow in or out?
Out.
Out. And therefore the cell shrinks. The good news is I did a really good job explaining that, and you guys all get it. The bad news is the College Board, if they say, explain what happened to the cell in terms of water potential, and you write, well, the salt draws the water out. Nope, no points. If you write, well, hypertonic solutions will make cells shrink. Nope, don't get points. If you write, the concentration of water is greater inside of the cell than outside of the cell, so therefore the water flows out because the salt cannot cross the membrane. Nope, you get no points. But if you write, the water potential on the inside is greater than the water potential on the outside because -2 is greater than -11, therefore the water will flow out, you get your points. Everybody with me? If they say, in terms of water potential, please explain this, you got to talk about water potential. You can't just say hypertonic, hypotonic. You can't just say concentration of water. You have to use the water potential language. And you got to remember that solute potential is always negative or 0. The highest it could be is 0. Oh, by the way, what solution would have a 0 solute potential? What liquid has 0 solute potential?
Distilled water.
Distilled water. Pure water is 0. It's the highest the solute potential could ever be. Anything that has anything dissolved in it has a negative solute potential. Where are we at? How we doing? Doing good? Okay. Got half an hour. All right, let's keep going. Let's do the next part. Yeah, the next part. This is the part that everybody gets wrong on the test, but you won't, because you're going to pay attention now. And you're going to remember this when I give you this question on the test. What? There's going to be water? Yep. Yeah, I told you right now, so I'm telling you ahead of time. I'm going to ask you questions like this on the test with pictures like this. Okay. All right. Now I want to know all of these numbers. This is before. This is after. After a long time of waiting, let's say we waited plenty of time that now everything is isotonic, everything is at equilibrium, everything is good to go. Nothing, no more net movement of water at all. The movement of water out and the movement of water in is now the same. Okay, that's the point we're at. In other words, this process has finished. Are people running around their place there? What's going on? So much movement. So now I want you to fill in these numbers. Okay, let's start with the easy part, the salt water. We said the salt water was -12 when we started. What's the salt water now? Giant beaker, tiny cell. What did the salt water, what happened to it? Did it change?
Not really.
No, not just not really, it really didn't change because remember peeing in Lake Michigan? Still not actually going to do that, but that's the example here is we got a little bit, a tiny bit of water added from the cell. Well, the cell is so tiny, it's like, that big. It didn't really affect the outcome. So this is, what is this, negative?
12.
-12. I would like unless there's a major lag between me and you here, I'd like the responses to come a little quicker. Maybe it's the internet. We'll blame the internet. It's not you guys, it's the internet. Pressure on the outside, atmospheric pressure, did that change?
No.
Did the Earth gravity magically change in the last 10 minutes? I don't think so. It's still 1. All right, so the water potential on the outside is -11. Well, that was easy. That part was easy. Inside now, here we go. Now we got to think. We're going to start backwards. We're going to do this backwards. I know if there's no more net movement of water this way and that way, what does this have to be? This was -2. It's not going to be -2 anymore. If there's no more net movement of water, if the amount moving out and the amount moving in is exactly the same, what does the water potential on the inside have to be?
-11.
-11 is right. -11 is right. And what did I tell you about pressure of animal cells on the inside? Or pressure of the inside of the animal cell is always what? The same as?
The outside.
Atmospheric pressure. That's still going to be 1. That didn't change. So now what is the solute on the inside here? Well, basically the question I'm asking is, what number plus 11 makes -11? X plus, no, not 11, I'm sorry. X plus 1 equals -11. What's X?
-12.
-12. -12 is right. Wait a minute, it's the same as this? Yeah, it's exactly the same. How is that possible? Salt can't get in. That's right. There was salt in here to start with. The salt that was in here to start with is all still in here. And the reason it's now at -12 is because we lost so much water that it got way concentrated in here. It's kind of like if you had a little bit of salt in water and you put a pot of this little bit salty water on the stove and you evaporated all the water off. But if you did that for 8 hours, wouldn't it get super salty? The answer is yes, it would. I'm not even going to wait for you. And that is it. It's going to go to exactly this. Because it's got to be -11 at the end because there's no more net movement. Because if this was not -11, let's say this was -8, what would still have to happen before it was done?
It still have to move, so it could
Water
be
would still have to move out if it was -8. So if it's finished and there's no more net movement, it has to be the same as the outside. So far, so good? Well, that's not that hard, Mr. Volk. You said it was going to be hard. That's because we didn't really do the hard part yet. Or maybe you do think it's hard. Well, then we got some issues. No, I'm kidding. It's not super easy. I understand the whole thing is a little weird. So, I get it. Okay, now we're going to do a cell in fresh water. So distilled water. Yay. Okay, well, let's cheat and see what the cell is. We'll do the same thing. -3, 1, -2. Okay, so this is still -3. This is still at 1. This is 1. This is -2. Okay, same as before. That's when we drop it in. So this cell has not been in here for any amount of time. We just dropped it in. So this is the beginning or before. This is the start of the experiment. Right at that moment, that's what the cell is. The solute is what out here? The outside solute potential. Keep in mind it's this. Pure water.
0.
0 is correct. Pressure is 1. What's the outside water potential?
1.
1. Is it called equilibrium? Yeah, so we could say these are at equilibrium or they're isotonic. Usually equilibrium is referring to one place, like inside of the cell or out, in one compartment. We don't usually say equilibrium between, if there's a barrier between with the membrane, but I know what you mean though, if you said that, like I don't really care that much about that definition, but all right. Okay, so here's what we got. We got a water potential of 1 and we got a water potential of -2. Which one is bigger?
1.
1 is bigger than -2. The water is going to diffuse in or out. Everybody together like a choir of angels now.
In.
And
Oh, that was so weak.
In.
Say it with passion. Say it like you mean it. Say it with love. Everybody together. I'm going to count to 3. 1, 2, 3, in or out.
In.
Much better. My God. It's like pulling teeth. All right. Water goes in, cell bursts, whatever. Or maybe the cell won't burst. Maybe it'll just expand a little bit. But in here, we said it bursts, so we're going to go with that. So we know this is 0. We know this is 1. We know this is 1. You might say, well, no, some solute diffused out. It went out, so this is not 0 anymore. Yeah, but it's going to be 0.0000000, go on forever, and 1 or whatever, like barely anything. So it's 0 for our purposes. All right, so inside here now we have reached equilibrium. We're isotonic. So this then must be 1. Pressure we know is 1. So this has to be
0.
0.
All right, so if you give it enough time, that's what's going to happen. Enough movement is going to be back and forth here that this is going to, all the salt's going to be basically replaced by water, and whatever tiny little bit of salt from the cell is out here is negligible. It's not worth mentioning. So if we were going to do it with, let's just for fun, if we were going to do it like this, you can see why I had these pre-made beakers, because my beaker drawing capabilities are not very good. Oh wait, I wanted to make it expanded. So let's say the cell does not burst. Let's say it's kind of like a skin cell or something, or muscle cell or whatever that doesn't burst because it has the extracellular matrix. So it just expands and gets real tight because so much water diffused in. So let's do this again. This is out is 1. So we said a whole bunch of water diffused in. And we said this was, in the beginning, -3. So what can you, and by the way, we know that the inside has to be 1 at the end, because there's no more movement. And that movement has stopped now. So now the question is, it didn't burst. There's still all the salt still in here, which means that solute potential is not going to be 0. So we have to make up a number. Is it going to be -4, or is it going to be more like -2? Which direction should I go? More negative or less negative? We added a bunch of water. We diluted it. Is it getting closer to 0 or closer to like -10? It started at 3. So we started here at 3. So there's a certain amount of salt. We should go less negative. So I'm just going to say 2.5, -2. Okay, hold on. I hate how it jumps around when I undo. Why does it jump? Okay, wish I knew what I was doing. So -2.5. Why -2.5? Because I added some water. I made it less salty, less concentrated. It's closer to 0. It's more dilute. Okay, if I know this is -2.5 and this is 1, what's pressure now? It's not 1 anymore.
1.5.
Say again?
1.5. -1.5.
That would give it negative 4 up down here, but it gives you 1. So if I do negative 1.5 and we add these together, then we end up getting negative 4 down here, but that's not what I got.
Wouldn't it be like
And by the way, pressure can't ever be negative. That's maybe something I should tell, I should have told you, but let's just think about it for a minute. Let's do a math problem like this. Negative, hold on, negative 2.5 plus what equals 1? Pulling out the calculators. 3.5 is correct. Whoever typed that in there, thank you, Elena Her. Very good. Negative 2.5 plus 3.5 equals 1. What does that tell you about what's happening inside of that animal cell? What's going on? That animal cell is used to 1 atmosphere of pressure. I'm sorry, 1 bar of pressure. What's going on with it now? Everything is like, what's that Queen David Bowie song?
under pressure?
Under pressure. Good song. Rest in peace, David Bowie. Rest in peace, Freddie Mercury. Well, that's depressing. Thanks for bringing that up, guys. All right. 2 really good singers, though, in my opinion. All right. So if it doesn't burst, you're going to get some pressure in here, which makes sense. Because now it's pressurized and it's all tight and everything and expanding. If it bursts, then it's all, equal to the outside. You never heard of Queen and David Bowie? Freddie Mercury? Are you kidding me? Dude, man. Sim, there's more than Justin Bieber out there. You should expand your horizons. There's more than just one direction, Sim. Can you just visualize Sim's like bedroom? The walls are like full of Harry Styles posters, life size, Oh my God, Harry Styles. He's so dreamy. Oh, can't even. I can't even. All right, what else we got? What's that you say? Plant cells? Yes, plant cells. Let's check it out. I don't know which one of these this is. This is not the right one. Is that the one? Oh, where is it? Okay, I gotta open it. Plant cells.
It was above the animal cell one.
Oh, here. Oh, yeah, it was this one. Okay. Now I should not draw on this one. Okay. I already had it open from the animal cell one. That's it. There it is. Ha, I knew I had this somewhere. I know what I'm doing. I'm a professional. Okay, plant cells. Yay. All right, here we go. Let's, what do we want to, you want to start with salt water? Is that what we've been doing? Let's do that, salt water. I think we started with salt water, right? So let's be consistent. Salt water, concentrated salt water. So let's say it's negative 12. Is that what we said last time? Yeah. It could be like negative 18, could be really negative, Easy with the chat now. Pay attention to this again. Otherwise, you're going to get lost. Pressure out here is 1 because it's just regular atmospheric pressure pushing down on the beaker from the air above us. And that we can't really control. That's just going to be 1. All right. So the outside water potential is going to be negative 11. Sorry, I almost wrote negative 12. It's negative 11 bars. All right. Solute potential inside of the cell we said was negative 3-ish. And that's about right for plant cells. I was going on about that before when I was actually drawing an animal cell, but whatever. That's a reasonable solute potential for a living cell. Okay, that's in the ballpark. There could be some variability there depending on the organism. The pressure inside of the plant cell, that one is kind of weird. When we first drop it in, the plant cell could be at a bunch of different states. If it's a healthy plant cell from a living plant that was doing very well, there ought to be some turgor pressure in there. It should start out with a certain amount of turgor pressure. So I'm actually going to say 2 for this, not 1. Why? Because plant cells actually are pressurized in the normal state, not animal cells, but plant cells. They are pressurized. Or, what is all this? Okay, whatever. Or if the plant was like, let's say you had a slice of potato or a leaf or whatever it was, and it was sitting out on the lab table for a long time. It was sitting there for a few hours. It was drying out. It was getting wilty. Then the pressure on the inside of the plant cell might be 1. So this is almost something that needs to be given to you. If somebody's going to ask you a question like this, you'd have to know the information about the plant cell. If it's a healthy plant cell doing its thing, the pressure, there ought to be some pressure, 2, 3, 4, something like that. I'm just going to say 2. Just going to make up a number. Okay. And then, so the overall water potential on the inside is what? So this is in. -3 plus 2. You math geniuses. Let's have it.
-1.
-1 bar. Okay. -1 is greater than -11. Therefore, water will diffuse in or out. Everybody together like angels?
Out.
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 It's going to go from high water potential to low water potential. High. Oh my God. What? I think that was a sign from God that I need to end class.
Yeah.
High water
Yes.
potential to low water potential. That's how water flows. All right, so water's going to flow out and the cell is going to shrivel again. Okay. This part is easy. This is still going to be -12. This is going to be 1. This is going to be -11. All right, so now if that's -11, we know this also has to be -11. We know the pressure because there's no more turgor pressure now. We've lost the turgor pressure. This has to be 1 now, so that changed. Which means the solute potential when it's all said and done has to be what? Basically what I'm asking is what number plus 1 is -11?
-12.
-12 is correct. Okie doke. So now we're at a point where we have equal water moving out and equal water moving in. There's no net movement of water, but the College Board likes to be tricky. They might say the flow of water has completely stopped. And that is not true. There's still water molecules moving out and there's still water molecules moving in. They're just equal numbers. No net movement of water. Because water molecules will still hit that membrane randomly and sneak through the phospholipids. They'll still squeak through there. And then other ones go in at the same amount. So there's no more net movement, but still some in both directions. All right, I've been talking about that for 10 minutes now, so let me move on. So this was salt water. Now let's go to, oh, by the way, is the salt water hypertonic or hypotonic?
Hypertonic.
Hypertonic. And the inside is hypotonic.
Potonic.
Okay, good. Same thing, but this time we're going to go distilled water, pure water. All right, so we know that solute potential out here has to be
0.
0. Pressure potential is 1. Overall water potential on the outside is 1. Easy. All right, this is a normal plant cell, so we're going to be consistent. We're going to do the same as we did before, -3. We're going to say this is 2, and we're going to say this is -1. So the overall inside water potential is -1. Which way is the water going to flow? What is greater, 1 or -1? The water is going to flow in or out? Choir of Angels, let's hear it.
In.
In. Thank you for the answer, by the way. I shouldn't be making fun of you. I want to hear everybody together. 1, 2, 3, in or out.
In.
Noah Washburn, you will pay for that.
You told us to sing on 3 or on 1, and I was in the middle of burping.
You. Only you would do that. You or Jack Tornio, and he's not in this class anymore.
Don't compare me to him. Please don't compare me to him.
Well, you're like the new Jack Tornio.
No.
I completely lost my train of thought. I got to start over. Okay, back to the beginning. We're going to be here till 3 o'clock today. Diffusion. Condensate took me. Yeah, I'm not actually going to do that. Okay, now we're going to wait enough time for this all to be done. We're going to let things happen. Water is going to diffuse in. We're going to give it plenty of time for everything to sort of equal out, and there's no more net movement. All right, so we always start on the outside if we're going to analyze this thing to make this easier. Okay, we got to start on the outside because that's still going to be 0. We already know this. Like, we start with the known and then we figure out the unknown. Okay, so we know when this is equal going across that the overall inside water potential, by the way, this is bulging a little bit now. This is under pressure now more than it was before. The turgor pressure has gone up. All right, so yeah, so overall this is going to be 1. And now let's figure out these other ones. Okay, so we know a considerable amount of water has gone in. And I said before, well, that little bit isn't going to affect it. Well, that's when we're talking about taking water from the cell and putting it in the beaker. Now we're taking water from the beaker and putting it in the cell. Does that make sense? We're taking water from the beaker and putting it in the cell. That's actually going to increase the concentration of water, but decrease the concentration of salt inside of the cell a measurable amount. So this might have gone down, if enough water came in here, this might have gone down to -2. This might have changed because it got more dilute. It's going to go closer to 0. So now we can figure out what's the pressure potential on the inside. What I'm asking you is -2 plus what makes 1?
3.
The answer is 3, which means now the turgor pressure on the inside of the cell has actually increased from 2 to 3. The cell is bulging more than before. It's got a higher pressure because that water that diffused in. All righty. So that's the way I want you to approach these kinds of problems. I want you to start with what's happening out here and then figure out what's going on in here. Coolness? We should do a worksheet, Mr. Volk, because we want to practice it.
No.
That's how you guys sound, by the way. How much time we have?
5 minutes.
Oh,
Wait, I
Yeah.
have a question.
can I
Are-
can I make you a deal here? On Tuesday, I'd like to do a lab with this stuff with you guys, and that means we might have to stay a little bit later. Is that okay?
I have a question about today. So
Yep.
you know how we have to do the partner, the group test thing?
Test
we-
analysis, I call it.
Yeah. Are we staying over today to do it?
You guys figure
or-
that out when it's best for you. Today would be a good time to do that.
Okay.
You can do it in my TSS if you'd like to. So I'm going to shut the Zoom down when the class is over, and I'm going to go into TSS. So you can come into the TSS and I'll make you a breakout room, or you can do your own Zoom. Do you guys have your Zoom? Like, do you guys ever start your own Zoom meeting? You guys have that ability? Or do you only ever join meetings? Well, you guys can
We
just
can
come in
start them.
mine and I'll
We
come
can
in
start
mine
them,
and
but they can
I'll
only be
give you a
like
breakout room to go into. I don't know how many freshmen I'm going to have show up. They have a test on Monday, but I don't know if any of them are going to come. So their test is pretty easy. So I don't know if they need it, but it might just be you guys. So talk to each other about that. Let me show you what the assignment is, okay? All right, let's take a look. Oh my goodness, I got a lot of stuff open here. Assignment is this. So I'd like, don't do the lab related one, do the water potential concepts before, after problems. Okay, so they're just like what we did now. I hope I didn't use the same numbers. That would be stupid because then you could just copy what we just did. I hope I used other numbers. Ignore the first page. We haven't learned this yet, so we're going to do this next time. So this is the part that gets a little funky here, but it's okay. It's not so bad. It's just math. We're going to do a bunch of math. We're going to do some graphing, and this relates to the lab too. Oh, I didn't give you any numbers. So what I'd like you to do is make up your own numbers, but not the ones I used. Reasonable numbers. Do like 2.7 or -3.5 or something like that, and then predict before and after. Okay? So I didn't give you any numbers, so you got to make up your own, but you can't use the ones I used, so you just use different numbers so you get used to this process. Basically, your So it says here distilled water. So you don't get to be too creative where it says, oh, this is Google Docs. I can't draw on this, but here where it says solute potential, you have to do 0 for the outside right here. Pressure, I would just go with 1 bar. You could be like super precise and you could do like 0.96 bars or something like that if you want to, but then it gets more complicated. All right, so then just do distilled for, these are plant cells, these are animal cells. Good to go. All right, so work on that on for Tuesday. Get this one done. Don't do the first page, just skip that and should be all right. What does he have? A pineapple?
This is a bromeliad.
Oh, I thought you had a pineapple. I'm like, what the heck?
No, it's a.
Why are you holding that? Is that your best friend or something?
Yes.
You go like to the movies with it?
No.
All right, any questions? Okay, now you give me some feedback. We got 1 minute. Was that complicated or not so bad?
Not so bad.
Okay. I mean, I did do a super great job teaching it. So like, if you had just like a regular teacher, it probably would have been a lot harder, but because you have me, it's like super easy. Yeah. Anyway, then the next part we're going to do with solute potential is going to be a little bit trickier, but it's not super bad. But then once we combine it all, once we combine everything, then it's all right. I think you guys will do well. We'll practice it quite a bit before we do a test on it. I've had too many kids lose points on this. I'm sick of it. So I'm trying to teach you guys this really well and give you tons of practice so that we don't keep having that issue. I feel like I'm forgetting to talk to you guys about something. Oh yeah, what about like AP test sign up? When does that do? I don't even know.
Isn't it due today?
Is it due today?
Yeah.
So did everybody
Yeah.
that's going to take the test sign up? Does anybody want to talk to me about whether they should take it or not?
I do.
All right, we can chat after. You can stay on for a little bit. But in terms of test sign up, if you haven't signed up yet, and if you don't get it done today, you can still do it next week, but they don't want you to know that. They want you to have it all done. The College Board will still accept the sign up from the school later, but try to get it done as soon as possible. If you're going to take the test, you got to go online and pay, okay? And whoever asked me about how to do that, did you figure it out? Whoever sent me that email, Hample, I think it was? You got to figure it out?
Yeah,
Did Mr. Williams help you?
yeah. I had to take. I signed up for it on AP Classroom, but I had to like sign up on Infinite Campus for like physics.
Oh, okay. See, I don't ever do that, so I don't know how to do it. Like, I never go to Infinite Campus and sign up because I'm not taking the test. Anyway, so my guideline usually is, well, when they make us decide this early, it's stupid because we don't really know how everybody's doing in the class yet because we only had one test. But my guideline usually is if you're passing my tests with A's and B's and C's, you should try to take the test. If you're failing my tests, probably want to consider not taking it and not wasting your money. But if we only had one test, it's hard to tell because maybe the first test was just a fluke and maybe in the next test, you're going to do super great and you should take it. So I don't want to like advise you against taking it and then maybe you could have done well. But anyway, if you are willing to put work into the class and learn the hard stuff, then do take the test. I know it's like 95 bucks and that's a lot of money, but in terms of the money it can save you for college credits, it's a good investment. All right. Is that it? I'll see you in TSS if you want to show up. Otherwise, I'll see you next week on Tuesday. Have a weekend. Bye. I'll stay on this Zoom for like 1 minute if anybody wants to talk right now.
Hey, Mr. Volk.
Sim the Dingus is still in here, so just say no. So you can hear what you're saying now. But go
No,
ahead.
I was just gonna ask about the retake.
Oh,
thing.
that, yeah. Well, I told you to come to TSS and we take care of it there.
Well, I just wanted to make sure because my teachers have been a little extra difficult this week.
That's what we do. We specialize in that. You studied, right? You learned the stuff?
Yes.
You didn't just keep telling me like, I already know it all, I already know it all, I knew it all then, I still know it all, I don't have to study. You actually studied?
Yes, Mr. Volk, I actually studied.
All right. Sim, why are you still in here, dingus?
I don't think
I
he's.
was gonna ask about the retake.
Oh, well, did you just hear what I told her?
I mean, yeah, with TSS.
What
I
did you
guess.
get, Sim?
I got like a 68%, and it was because like I think I just forgot some little details on like the writing parts, and so that's what messed me up.
So you got a 2 like a developing?
Yeah, I think.
That's
Yeah.
not that bad. I'm not going to give you a retake for that. That's not that
kidding me?
terrible. Huh?
Wait, like there's no way I can get my grade up then?
Yeah. Do a good job on the lab.
Wait, but
Do a
that's
good
like
job
the
on the lab. Did
ultimate
you turn the lab
grade.
in even? I think you're missing it, aren't you?
What do you mean?
Did you turn the lab in?
I finished the lab. I just gotta finish that one lab right up. That's the only thing I have left.
Yeah, so the lab that was due a week ago, you still don't have done, and then you're telling me about wanting to get your grade up? Get out of here, man. That's silly. You're not even turning the stuff in you're supposed to be turning in, and the lab is a huge part of the grade. That's graded. That's summative, man. Evidence.
Okay.
All right.
Yeah.
All right. If you want to come to TSS, go ahead, but I'm not. I'm not giving you a test redo. We're good on the next one. All right, just leaves without saying goodbye. That's great.